In this video, we're going to look at the sum and difference formulas. We're actually going to pick the sum and difference of sine alpha plus beta. We're also going to look at the sum of cosine alpha plus beta. And we're also going to look at one of the two tangent sum and difference formulas. We're going to look at the difference of alpha minus beta. Now, what's going to be interesting about this setup here is that, first off, these two values for alpha and beta are actually not on the unit circle. They're not on the unit circle, but they are actually some pretty easy ones to follow here, and we're going to draw some triangles to show where they would exist. Now, the first alpha is between pi and 3 pi over 2, which is between 180 and 270 degrees. So that would be in the third quadrant. And this would be the triangle drawn in the third quadrant from alpha. Now this alpha right here has a tangent of 5 over 12, which means that, according to SOHCAHTOA, the tangent is opposite over adjacent relative to alpha. But since we're in the third quadrant, these are going to be negative values, because this is a negative y value and a negative x value. Now, to find the missing side here, we would use Pythagorean theorem. Pythagorean theorem would be the a squared plus b squared equals c squared, or in this case, x squared plus y squared equals h squared, or the hypotenuse squared. So the x is negative 5 quantity squared, the y is negative 12 quantity squared, and that's going to be equal to h squared. So this is 25 plus 144, and then those added together is 169, and that's equal to h squared. Now, what we're going to do is take the square root of both sides, and taking the square root of both sides gives me a plus or minus 13, because 13 times 13, whoops, sorry, I don't need the square root on that. Take that off there. So this gives me, after I took the square root of both sides, plus or minus 13 is equal to h, and we're going to consider our hypotenuses as positive. This has been the technique I've been using in my class, and this is now my reference triangle for alpha. I am now going to find the reference triangle for beta over here. I'm going to move to this problem here. It looks like I too am also going to be again in the third quadrant, so that would be the one from 180 degrees to 270. So I'm going to draw a triangle in the oops, sorry. These are supposed to be right triangles, as this one's supposed to be a right triangle as well. Sorry, just drew that a little skew there on my tablet. And this is beta. And according to sine is, according to SOHCAHTOA, the opposite over hypotenuse. And because this is in the third quadrant, this y value would be negative. So we need to find this missing x value, which also will be negative. So to do that, we're going to use Pythagorean theorem again, but instead of a squared plus b squared equals c squared, you can see me writing down x squared plus y squared is equal to h squared. So the x value is unknown, so we're going to solve for that. The y value in this case is negative 1 quantity squared, and that's equal to the hypotenuse squared. Then what we will do is we will square the 1, which gives me a positive 1. And the hypotenuse, I should have written in there a 2. I can quickly do that with my eraser. Just take that out there. And in place of that, I'm going to put a 2 there, 2 squared, and that's going to be 4. Subtract 1 from both sides. X squared is equal to 3. And then take the square root of both sides, like so. Now I have x is equal to plus or minus the square root of 3. Now, because the x value here is going to be in the third quadrant, that x value is going to be negative. So we will choose the negative value here, and this is going to be the negative square root of 3. So these are my two reference triangles. I will use these two triangles to with the sum and difference formulas to get those values and then solve for these exact values. There are no calculators to be used at this time, and if you do use a calculator, it will be a simple 10-digit calculator with addition, subtraction, multiplication, division. And it, for some of the bigger numbers that will show up for part D of this problem. So let me actually make some room here. I'm going to erase the work I did here. And the reason why is I want these reference triangles to stay on. I want these reference triangles to stay on the screen here, because I'm going to use them as I go through parts A through D. Okay, so starting off with part A. Part A is going to be the sine of alpha plus beta. Now, the sine of alpha plus beta is written as the function, written as the formula, sine of alpha cosine of beta plus cosine of alpha sine of beta. Now, you've probably seen these formulas maybe in different books or the edition that I'm using. You may see these written in a different way. The reason why I like to teach them in this orientation is that this way your alpha beta stays in the same order. So your equation will always have alpha beta in it. Again, you can write this different ways using the commutative property, so it could be alpha beta alpha of sine alpha cosine beta plus sine beta cosine alpha. I just prefer this method. Now what this means I'm going to do is I'm going to look at my alpha triangle and use the sine value, get the sine value of that. And the sine value, according to SOHCAHTOA, is negative 5/13. So this is the sine value here. The cosine value is going to be then from this triangle, and according to SOHCAHTOA, it's adjacent over hypotenuse, or negative square root of 3/2, plus cosine alpha, plus cosine alpha, and I'm going to again go to my alpha here and go cosine, which is adjacent over hypotenuse, so this is negative 12/13. Oops, come on, buddy. And sine of beta, go back to my beta triangle and go negative 1/2. Alright, so I got all those done. So now what I just need to do is multiply these together. Top times top, bottom times bottom. The first fraction is positive 5 square roots of 3 over 13 times 2 is 26. And then this fraction here is top times top, bottom times bottom is 12 over 26 again. Now we can. There's many different ways to write this answer. I want to highlight the fact that the book is going to combine the numerator since we have common denominators. Though I prefer to keep these separate in case simplification can occur. So we will rewrite the order of this because I like to have the rational in front, then the irrational and imaginary in back. So this would be reduced to 6/13 plus 5 square root of 3 over 26. So this would be my final answer here. Now obviously the book will have this written as one numerator over one denominator, though I would hesitate that I don't want anybody in this room simplifying the 12 and the 26 this way. You can only do it when you split them up into separate pieces. If you have this as your final answer, you can't do any simplification of that first term. Texas Instruments calculators prefer the A plus BI format where you have your rational, irrational, and imaginary, though we've seen in previous books where they've had rational, imaginary, then irrational afterwards. Again, that's based on the book that you might be using, but I like keeping it to the A plus BI format that's common on the TI Texas Instrument calculator. Now, it would behoove us to actually do part C next, just because part A and part C, the only difference is a plus and a minus, and so the only difference in the equation for this would be a minus. And that means we can actually do the problem much quicker. I think you're going to find doing the homework is going to be faster if you do part A and part C side by side or right after each other, because then you can see that this whole thing is going to have just a subtraction in the middle. So I'm starting off my 5 square root of 3 over 26 minus 1226. So that's the only difference between the two of them. So what we will do is just rewrite the problem again with the negative 1226 in front, or in this case negative 6/13, plus 5 square root of 3 over 26. And this is now 2 parts of my 4-part problem. We're going to now do part B, and I'll pause this to clear this out, and we'll start part B in just a second. So for part B, we are going to take the cosine function. Whoops, got to get my stylus turned on there. So cosine of alpha plus beta is equal to, and again you might see some different functions based, or different formulas based on what book you're using, but here I have my cosine alpha, cosine beta, minus, these are opposite symbols here. The plus is a minus, the minus is a plus, and then I have sine of alpha, sine of alpha, sine of beta. Okay, so let's plug some stuff in here. We'll go to my alpha triangle. According to cosine, cosine is adjacent over hypotenuse, so this is negative 12/13. And the cosine beta over here, this is negative 3 square root of 3 over 2. And the next thing we'll do is we'll subtract the sine of alpha. The sine of alpha is over to my alpha triangle, the negative 5/13. And the sine of beta over here is negative 1/2. Then we multiply these two together. This is just simple order of operations. We'll have a positive 12 square root of 3 over 26. Notice that this can be reduced. We are going to reduce this. And then this here, this is a positive, because two negatives make a positive. This is still a subtraction sign there, but this is going to be 5/26. So in this case, I'm going to reorder this again. I'm going to put my negative 5/26 in front. Do that because I like to have my rationals in front, rational, rational, imaginary. And then what we'll have is a positive. That 12/26 reduces down to 6/13, square root of 3. And that is my final answer for part C. Now, part D is probably going to take us the most time out of all of these. So the tangent, making sure I got my pen here, the tangent of alpha minus beta is the function, sorry, the formula, tangent alpha minus tangent beta divided by, and here's where things can get a little trickier, 1 plus, not minus, but 1 plus tangent alpha times tangent beta. And what's going to make this problem or equation tricky is when the alpha and the beta have a radical in it. If either one of those is a radical, we're going to have to actually get into pretty deep college algebra to simplify this properly. Okay, so let's get this started. We go to my alpha and we look at the alpha minus beta, which is going to be negative 5 over negative 12, which two negatives will make a positive. We'll simplify the next time. And then over here we're going to have minus negative 1 over negative square root of 3. Alright, so that's my numerator, and then my denominator down here is going to be 1 plus, and that's going to be the negative 5 over negative 12 times the negative 1 over the negative square root of 3. Well, let's do some simplification. Let's kind of first of all work in the numerator for a moment. The negative 5 over negative 12, that just makes 5/12. No surprises there. This negative 1 over negative square root of 3, I'm going to do a little bit of work here, and the reason why is because I don't really like a square root in the denominator. So not only do these two negatives make a positive, but I'm going to multiply top and bottom by square root of 3 over square root of 3. I will show that by quickly changing color here and multiplying square root of 3 by square root of 3 and changing back to my other color. That would then make this a minus square root of 3 over 3. And that is going to give me, so far, my simplified numerator. Now, I haven't gotten common denominators yet, so what I'm going to do is take that second fraction again. I'm going to multiply by 4 over 4. And the reason why I'm multiplying by 4 over 4 is if I multiply the 3 times the 4, I get a common denominator. And my common denominator is going to be now 12. So my numerator is now 5/12 minus 4 square root of 3 all over 12. So this is my new numerator. And I still haven't done anything with this denominator yet, but I wanted to show you that this is going to make something in college algebra we called a complex fraction. This is going to be like a fraction over a fraction. But what's great about this is that we're actually going to be able to do some pretty good simplification with that. So let's now focus on this denominator now. This denominator is going to be 5/12 times the negative 1 over the square root of 3. A couple things here is that I do not want this, first I want this to be just a normal 5/12 and the normal 1 over square root of 3, but I'm going to do the same thing by multiplying the second one by square root of 3 over square root of 3. And that's going to turn this thing into that square root of 3 over 3. Now if I go top times top, bottom times bottom with these two subtract or negative signs turning positive, now what I have is I have 1 plus 5 square root of 3 over 12 times 3, which is 36. This also means that I'm going to have to take this 1, because this 1 doesn't have a denominator, and get a common denominator, and I will do so by multiplying 36 over 36. And what that will then give me is that will then give me 36 plus 5 square roots of 3, all divided by 36. So it looks like there's still like a lot of work to do here, and there is, because what we now have is a complex fraction where we have a numerator divided by a denominator. Now dividing fractions, please don't cry, just skip, flip, and multiply. So we're going to take that 5 minus 4 square roots of 3 divided by 12. We're going to skip that fraction, flip the second fraction, and by flipping the second fraction, we're then going to get to multiply. So that 36 is now in the numerator instead of the denominator, and now we have 36 plus 5 square roots of 3. So what's cool about the 12 and the 36 is that these are divisible. They both can be divided by 12, which means that this is going to be a 1 and this is going to be a 3. Come on, write my 1. There we go. And so this 3 then gets multiplied by this numerator, which is going to be 15 minus 12 square roots of 3. And this denominator down here is going to be 36 plus 5 square roots of 3. Well, now you would normally just say, oh, well, great, I'm done with the problem because I've now gotten as far as I can. I can't pull out a can't pull out a factor of 3 in the denominator to simplify with the numerator, so I'm done. But unfortunately, you're not done. And the reason why you're not done is because we do not like radicals in the denominator. And one of those skills that we learned in college algebra is to multiply by the opposite binomial to create a difference of squares pattern. So what we will do is multiply the top and bottom by 36 minus 5 square roots of 3 and 36 minus 5 square roots of 3 here. So we're going to do a little FOIL action in the numerator. I'm going to get my pen ready because this is going to be kind of a long 4-term problem. And this is where you would get out your super simple calculator, and it's super simple because we want it to basically just take care of just simple transactions. So again, it will be a 9-digit calculator, and that 9-digit calculator will get you 10-digit calculator will get you exactly what you need without giving away the answers. So 15 times 36, again this is going to be my FOIL part here, so 15 times 36 is going to give me 540. 15 times negative 5 square roots of 3 is going to give me negative 75 square roots of 3. This negative 12 square root of 3 times 36 is going to give me negative 432 square roots of 3. And then this times this. Now this is interesting because the negative 12 times The negative 5 is going to give me a positive 60, and the square root of 3 times the square root of 3 is going to give me a 3, so this is going to be 180. Now, my denominator, the fun thing about that is that I could do all 4 FOIL cables, but really I'm only interested in the F cable, and where I do the first terms, and the L cable when I do the last terms. And the reason why is the O and the I cables, they will simplify to 0. Because if I go 36, again, if I'm looking at the outside cables, this would give me a negative value of 36 times negative 5 squared root of 3, and the inside would give me a positive value of 36 times 5 squared root of 3, so those simplify to 0. So really I only concern myself with 36 times 36, and that's going to be 1,296. Now the 5 squared root of 3 times negative 5 squared root of 3 is negative 25 times 3, because the 5 times 5 is 25, that being a subtraction in the middle, and square root of 3 times square root of 3 is just 3. So if we now do our simplification of the numerator, if I add my 540 and my 180 there, I get a total of 720. If I subtract 75 square roots of 3 and 432 square roots of 3, what I now get is 507 square roots of 3. All divided by this 1,296 minus 25 times square roots of 3 is 1,221. It does benefit us, though, if you take a look at the 720 and the 507 and all these numbers here, you'll note that these are divisible by 3. So, since you know that the 720, the 507, and the 1,221 are all divisible by 3, what that allows you to do, it allows you to make the problem 3 times smaller. So 720 divided by 3 is 240. The 507 divided by 3 is 169. And the 1,221 is divisible by 3, so that's 407. Now, you may not have realized why this is divisible by 3, but I should bring up this kind of cool piece of numerological fact, that if the digits in any number add up to something that's divisible by 9, it can be divisible by 3. So, for example, 7 plus 2 plus 0 adds up to 9. That's divisible by 3, so you can divide it by 3. If the numbers are divisible by 3, you can divide the whole thing by 3. For example, 507 add up to 12, so that's divisible by 3, and 1221 adds up to 6, so that's divisible by 3. It's kind of a cool little trick there. So this is your end problem, and now you can see that part 4 of this problem, this tangent sum and difference formula, has actually the most complicated algebra of all of this. So for the second half of this video, we are going to now do this 4-part problem here. You kind of maybe noticed that there weren't a lot of problems assigned in this homework section, but that's because each problem has multiple parts to them. So even though you may have only received 10 to 20 problems, that's probably 40 problems or so. So it's wise to get started on this homework right away. But the first thing I'm going to do is I'm going to investigate alpha and beta and figure out which quadrants they are in, and after I figure out which quadrants they are in, I am going to draw their perspective triangles. So I am now looking at this cosine alpha, and alpha is between negative 90 degrees, or negative pi over 2, to 0. So that puts us in the 4th quadrant. A 4th quadrant triangle is going to look like this. And there's your right angle, and here is your alpha. So there's my alpha. The alpha is 1/2 of cosine. So the cosine, according to SOHCAHTOA, is going to be the adjacent over hypotenuse. Now to find our missing value we're going to find our missing value y here. We're going to find that missing value y by using our, and y is going to be negative because I'm in the 4th quadrant. We're going to use our, Pythagorean theorem again. X squared plus y squared is equal to h squared. So what do we know? We know our 1 squared, we know our h as well. So that's going to be 2 squared. So that's going to be 1 plus y squared is equal to 4. Then we subtract the 1 from both sides, y squared is equal to 3. Take the square root of both of these, and that gives us y is equal to plus or minus the square root of 3. Now, because we're in the fourth quadrant, this is going to be a minus. So that y, if I use my eraser here, beep, I will then, getting back to my pen, make this a negative square root of 3. So this is my alpha triangle that I will use for the 4 parts of this problem. Now I'm going to go over here and make my beta triangle. My beta triangle, my sine of beta, it looks like I'm going to be between 0 and positive 90 degrees, or pi over 2. So that puts me in the first quadrant. And this is what a first quadrant triangle would look like. And here's my beta. And now, according to sine is, according to SOHCAHTOA, opposite over hypotenuse. So I need to find this missing side here. So again, using my x squared plus y squared equals h squared. And everything's going to be positive in the first quadrant, so we do not need to concern ourselves with negatives after we take the square root. But we're going to have 1 squared plus y squared equals 3 squared. So that gives us, come on, give me my, there we go, 1 plus y squared equals, I have to be a little bit more deliberate when drawing with this pen, 9, okay, because that's 3 squared. Subtract 1 from both sides, y squared is equal to 8. Take the square root of both sides, and this does give me the plus or minus over here, but we're going to choose the plus option. Y is going to be equal to the square root of 8. But notice that the square root of 8 is actually simplifiable. According to College algebra rules, if we have a square root, we're going to look inside to see if there is a number we can remove from that using multiplication. And the number we're going to try to remove is a square rootable number. So 4 happens to be a square rootable number, and the square root of 4 times square root of 2 is square root of 8. So that would make 2 square root of 2 the simplifiable version of square root of 8. So this y value is going to be 2 square roots of 2. And these are my 2 values now, my negative square root of 3 that I found and my 2 square root of 2 that I found to finish up alpha and beta to use for these 4 functions. So now that I'm back to looking at my 2 finished triangles, I'm going to do part A and part C back to back because that seems to be the fastest way to do them. And so I'm looking at the sine of alpha plus beta. So this is going to be the sine of alpha cosine of beta plus, and the symbols match. I said plus. The symbols match actually the formulas themselves, and this is going to be then cosine alpha sine of beta. So I'm going to load that up. I'm noticing that on my sine, I'm going to have the opposite over hypotenuse, so negative square root of 3 over 2, multiplied by cosine of beta, which is 1/2. Now I'm going to then look at cosine alpha sine of beta. So, wait a second here. It's not 1/2. It's, I was on the wrong triangle. Okay, let me back this up again. Sorry about that. Luckily I have, oh no. Quickly get my stuff back. This is the one I wanted to erase. Alright, let's try this again. So, that's my sine of alpha, cosine of beta. I go to my beta. My beta is going to be my adjacent over hypotenuse. So this is 2 square root of 2 over 3. That's better. And now I'm going to go to my cosine alpha, which is 1/2. And my sine of beta is going to be 1/3. These are using all the SOHCAHTOA rules. And I'm sorry I made a mistake there, but you have to switch between alpha triangle, beta triangle, then alpha triangle, beta triangle. Now let's just do some simplification. Top times top, bottom times bottom. This is going to be a negative 2 square root of 6, all divided by 6. And we can simplify this fraction. This is going to be 1 times 1, which is 1 over 6th. And what I would do is I would switch the order of these because I like to have my rationals in front and then my irrationals in back. And the 2/6 makes 1/3, but please make sure to not put the 1 up top here. We don't say 1 square root of 6. Square root of 6 is the simplified version of that. I'd have to take a point off if you left the 1 up there. Now, again, my book is going to do it this way. It's going to put the 1 minus 2 square roots of 6 all divided by 6. So you'll see this in the back of the book. You'll see this on TI and TI calculators. And again, they're both equivalent. It's just that I like this a little bit better because it again matches your technology, and also it's reduced a little bit more. Now I'm going to do part C, which would be just changing the plus to a minus in this case, and that would just give me a negative 2 square roots of 6 over 6 minus 1/6. So again, if I was going to use it the way I did, I'm going to then move this in front, which is going to be a negative 1/6. And come on, and then this is going to be a negative square root of 6 over 3, because 2/6 is 1/3. And those are my answers for A and C. And again, the book would have the negative 1 up at minus 2 square root of 6 over 6 for part C's answer. So for part C, we are now going, come on, give me my pen. For part C, we are going to look, part C, we just did part C. For part B, that's what I'm talking about. For part B, we're going to look at the cosine, the cosine sum formula. So this would be the cosine alpha, cosine beta, minus sine alpha, sine beta. All right, so then let's actually go to the alpha cosine is going to be 1/2, because that's adjacent over hypotenuse. Cosine beta over here is going to be 2 square roots of 2 over 3, minus the sine of alpha, which is going to be negative square roots of 3 over 2, and the sine of beta, which is going to be 1/2, or 1/3, excuse me. All right, so let's kind of combine these two together by multiplying top times top, bottom times bottom. That's going to be 2 square roots of 2 over 6, and we're going to go plus in this case. And the reason why we're going to go plus is because we have a negative and a subtraction sign, and that's going to give me square root of 3 over 6. And actually, I like to stop right there. The book will combine both of these numerators over one denominator, and since there are two irrationals, square root of 2 and square root of 3, there's really no huge precedent over which one should be written first. And some of your instructors may want you to put like maybe the highest one first or the lowest one first. I just feel like this is really as far as we can go, except I would simplify that first one though. Instead of 2/6, I would make that into 1/3, and that would finish that up for me right there. Because you can, have a reduced fraction, which is pretty great. So that is going to give us our answer as far as we can go. Now part D, which is the tangent function, woo doggy. If you thought the last one was rough, man, you should check this one out because we have more than one radical in this case. So buckle in, folks. The last part of this... Oh, my laundry's done. While I change my laundry, I'm going to kind of psych myself up for doing this last problem here, which is going to be a doozy. So part 4 of this problem is our good old buddy tangent. And our good old buddy tangent, the difference formula here is going to start off with the tangent of alpha minus the tangent of beta, all divided by 1 plus tangent alpha times tangent beta. So let's look and see how that loads up. Go to my alpha triangle. My tangent of alpha is opposite over adjacent, so negative square root of 3 over 1. Now, I never, ever have that 1 in my final answer, but I want you to see how all of this shakes out. Then we're going to subtract on our other triangle here, opposite over adjacent, so that is going to be 1 over 2 square roots of 2. This is my numerator of my difference formula here, and then my denominator is going to be 1 plus the negative square root of 3 over 1 times the 1 over 2 square roots of 2. Now, I don't like having a radical in the denominator, so I'm going to multiply the top and bottom of this problem by square root of 2 over square root of 2. And what that's going to give me, that is going to give me a negative square root of 3 over 1 minus square root of 2 over 2 times 2, which is 4. Now to continue on with my numerator is I'm going to take this first fraction, since they do not have common denominators, I'm going to multiply that by 4 over 4. Now if I do that, that is going to give me now a numerator of 4 square roots of 3 minus square root of 2 all over 4. Now, it's quite a numerator, wouldn't you say? I would say so, and I shouldn't forget my negative here on the front, because that was a negative in the beginning. So that is going to be my numerator of my whole fraction. See, this is another complex fraction. We're going to have a fraction over another fraction. So let's kind of combine these together. So here's what I have. I've got 1 plus a negative square root of 3 times 1, which is going to be just negative square roots of 3. And in my denominator, the 1 times 2 square roots of 2, so this is just 2 times square root of 2. Now again, I don't like having a square root in the denominator, so I'm going to multiply this fraction by square root of 2 over square root of 2. Oh, what happened there? That was weird. Let's see if I can get rid of that. There we go. Okay, so again, square root of 2 over square root of 2. And so that will give me a new denominator of 1 plus this negative square root of 6 all over 2 times 2, which is 4. Now I still have to work a little bit more because I want to get this common denominator in my denominator. So I'm going to make that 1 a 4 over 4. Multiply by that 1 by 4 over 4. And so what that gives me in my new denominator here is it gives me 4 minus square root of 6 over 4. And over in my numerator, and I'm just double checking my work here just to make sure I didn't make any mistakes. Nope, looks good. I've got a negative 4 square roots of 3 minus square root of 2 all over 4. And so I have a fraction divided by a fraction. So dividing fractions, please don't cry. Skip the first fraction. That's 4 square roots of 3 minus square root of 2 over 4 times the 4 over the 4 minus square root of 6. So simplifying, the 4's completely simplify. So now we are left with a fraction of negative 4 square roots of 3 minus square root of 2 all divided by 4 minus square roots of 6. Well, so what do we do now? Because it seems like we're done, but unfortunately we're not quite done with the problem. And the reason why is because we have a radical in the denominator. We don't like keeping radicals in the denominator, so we're going to multiply the top and bottom by the opposite of this binomial here. So this is 4 plus square root of 6 and 4 plus square root of 6. Multiplying by this fancy 1 is going to give us a wicked FOIL problem in the numerator. Let's kind of FOIL this out here and show you what the first, outside, inside, last cables look like. So taking those in order, if we go the first cable, this is going to give me a negative 16 square root of 3. Then the second cable is going to be a negative 4 square root of 18. Then the inside cable here, this is going to be negative 4 square root of 2. And our last one is going to be negative square root of 2 times square root of 6, so negative square root of 12. All divided by, now again, we could do all 4 cables here, but noticing that the O and the I cable will just be opposites and simplify to 0, such as the 4 times the negative square root of 6 and the 4 times the positive square root of 6 will be 0. So the only cables I concern myself with are the first cables, which gives me 16, and the last cables, which gives me the minus 6, because square root of 6 times square root of 6 is 6. So let's do some combining of like terms. In my numerator, if I combine, if I actually do not really any combining right now, let's just look at simplifying some of these right here. I'm going to highlight the fact that this and this, these are simplifiable radicals. The 4 square root of 18, I'm going to write that in over down here after the 16 square roots of 3. That 4 square root of 18, that 18 can be broken up into 9 and 2, and the square root of 9 is 3, square root of 2 is square root of 2, so 3 times 4 is negative 12 square roots of 2. The 4 square root of 2 stays the same. And again, the square root of 12, we're going to have that as 4 and 3, and so that is going to make a 2 square roots of 3. So this again is my numerator, and my denominator, 16 minus 6, is just 10. Now what I can do here is combine more like terms. The 16 minus the 16 square roots of 3 and the negative 2 square roots of 3 is negative 18 square roots of 3. My negative 2 square root of 2 and negative 4 square root of 2 is a total of negative 16 square roots of 2, all divided by 10. Now you'll notice that the 18, the 16, and the 10 are all even numbers, so they can be divisible by 2. So if I divide these by 2, I get negative 9 square roots of 3, minus 16 divided by 2, 8 square root of 2, all divided by the 16 minus 6, which is now going to be a 5 in my denominator. And the reason why it's going to be a 5 because I divided everything by 2, and that gives me my final answer of the problem. Oh, that was pretty intense. But that got us to where we needed to go for the end of the problem and the end of this very long page. So what was really challenging about this? If I have to give you my 2 cents, what was really challenging is all the college algebra. It really wasn't too bad getting a formula and looking at our simple triangles that we learned back in the first unit of this trigonometric class that we've been using. But boy, oh boy, remembering all those rules from college algebra can sure be a lot of work. So I appreciate you making it through this long video, and thanks again for watching.